Good morning, students. Am I audible?
Yes, ma'am, you're audible.
See, I have class around 11. So make it fast. All of you join.
Yes, ma'am.
Who is going to share the PPT? Who is going to show the demo?
Uh, Ma'am, I will be sharing the code.
See, your voice
Demo.
is not audible. Raise your voice.
Uh, uh, Am I audible now, ma'am?
Voice.
Hello.
Okay. Start sharing.
Yeah, ma'am. Is the screen visible?
No, I can just see.
Okay. I hope it's visible now. Yeah. So good morning, ma'am. So now we have implemented the code using the GAN network, which is the type
Increase
of
your
ML.
volume. Volume increase.
It is on like the highest I could have. Like my mic volume is on the highest. Um, Also.
Okay.
Um,
Start.
yeah, so we had implemented our code using GAN, which is a type of ML consisting of two neural networks that work against each other using generator and discriminator. And generator, it creates the synthetic data which resembles the real data and it learns to map a random noise, whereas the discriminator, it determines whether given data from the data set is real or the fake which is generated from generator. And networks, they are trained together, wherein the generator tries to fool the discriminator and discriminator avoids being fooled, and over the time generator improves to produce realistic outputs. So in our code, GAN is used to generate musical piano rolls, which is representation of piano, and they are conditioned on harmonic structures, that is chroma features. So again, I'll explain chroma features and the purpose is, so chroma features actually serves as harmonic guides for GAN, and it generates piano rolls, providing GAN with chroma structures, and it ensures that the generated music, it aligns with the harmonic constraints. Starting with the first line of the code, which is pip install pretty MIDI, and it's a library that allows us to work with the MIDI files, and it includes reading and writing, manipulating of the data. Then we have the Librosa. The Librosa is a popular library for audio and music analysis, and it provides tools for feature extraction. Then we have Pretty MIDI. So this enables the use of to interact with the MIDI files and extracting piano rolls. Then we have the reverse piano roll, which performs transformations on piano rolls. Then we have the NumPy, and NumPy is used for again the numerical computations and creating and manipulating the array. The next we have is the TensorFlow. So TensorFlow is used to build and train the GAN model, and it defines neural networks, optimizes the loss function, and manages placeholder for input data. Then we have the Matplot library. It is used to visualize generated output and image during debugging and analysis. Then we import the OS again to interact with interact with the OS and create directories. Then we have the get songs. Wherein we define the path and we extract the piano roll representation from our MIDI files in a specified folder and pre-process them to train the GAN model and ensure input data. Then, as said that chroma functions, we use get chroma to extract the chroma features from each songs. Then we again mention the path here for the zip of the zip file that contains our MIDI files into the directory, so they are readily accessible. And the lastly, we have get songs here, which and the code prepares here the data set by processing the MIDI files into piano roll representatives and chroma features, which is both very crucial for input data. Over to you, Alyssa.
So before we're setting up the GAN model, we're defining some variables and parameters. So the lowest note and the highest note is 0 and 78, and that will be the range of the notes in the piano roll. So the number of the range that the model will consider to be on a piano roll is 78, and we're defining the number of units per that will be on each layer. So in the input layer, it will be xdim and zdim, and the number of units in the hidden layer will be 50.
See,
And below,
Elizabeth, I cannot able to hear anything from you. Okay, total your side.
uh,
My volume is full, 100% I kept. Still,
and
your voice is now. I cannot able to hear anything. Okay, why to waste time? You please come and present on in person. Okay, I'm telling you, I cannot able to hear anything. Simply, you people are.
ma'am, can you hear me now? Am I
Yeah,
audible?
Alyssa, you are audible. Yes, you are audible now.
What?
Ma'am, can you hear
Yeah,
me now? Like, I changed my audio, my headphone, and I'm speaking from the
Yeah, I
laptop.
cannot able to hear anything from you. Okay, that's all. You tell someone somebody else to present.
Okay. Anushka, can you speak?
okay, fine. So yeah, ma'am, am I audible? Okay, so here we, as said, that we have taken the lowest node as 0 and the highest node as 78, because and then we have defined the range of the MIDI file. Then we have taken the number of steps equal to 4, and this controls the temporal resolution of the input sequences. Then uh, going on to importing the tensor flow, and now we have the placeholder for the input data, which is xdim is the dimension of input data, and it allows the flexible batch sizes during training. Here, as we can see, we have introduced the first layer of the discriminator, that is d underscore w1, and the purpose is that it has initializes the weight of the first layer discriminator during the Xavier analyzation. Then the d underscore w2 is the second layer of discriminator, and the purpose is to that it initializes the biases for the second layer with zeros. Next is the first layer of generator, that is g underscore w1. It initializes the weight again for the first layer and with zeros. The second layer of the g generator is introduced as g underscore w2, and the purpose in this is it takes random noise z, which is introduced as z, and maps it to data space, which is introduced as xdim. And next we have we define, so the here the generator function gets defined and a forward pass in the generator model, and it takes random noise z as input and produces the data resembling music, which is the job of generator. The gh1 it computes the output in the of the first hidden layer, and in this computation the tf dot matmul z and g underscore w1, it multiplies input z with weights of the first layer and adds biases g underscore b1. So the purpose of this in our code is that the architecture here, it consists of a hidden layer with ReLU activation function to learn complex patterns. Nextly, we define the discriminator, and the discriminator further defines the forward pass, wherein there's again a hidden layer computation, and the discriminator function evaluates whether the data x, as we can see, data x is combined with conditional information c to determine whether it's real and or fake. Now we have the plot function here to visualize the output samples, that is either the generated piano or the chroma features in the grid basically. So the purpose of this in our code is that it is designed to visualize generated outputs and provide an organized way to compare multiple samples. Next, we have the loss function here. So I'll explain this. I'll do a step by step breakdown. So the first one is discriminator real loss. It measures how well discriminator classifies real data, like the data set, as real. So next is discriminator fake loss. It measures how well the discriminator classifies the fake data. And next we have the total discriminator loss, which is d underscore loss equal to d underscore loss real plus d underscore loss fake, which combines the losses for both real and fake classifications. And the aim is to minimize this loss to improve its classification accuracy for both real and fake inputs. Next we have the generator adversarial loss, which is the fake loss. It measures how generator fools the discriminator into classifying its generated data into real. Then we have the generator L1 loss, which measures between the real data and the generated data. For example, it can be a G sample as given as we have taken here. Then the total generator loss is calculated by G loss equals to G underscore loss plus 100 into G underscore loss L1. Again, the purpose of this is to distinguish and learn between. So the discriminator learns between the real and fake data, while generator also with time learns to produce more realistic fake data. And the L1 loss, it ensures that the generator output aligns closely with real data, enhancing the quality of the generated samples, while the optimization target, that is the D loss and G loss, it updates during the training, and the discriminator minimizes the DLoss while the generator minimizes the G loss. Next, training the GAN model.
Hello, good morning, ma'am. Yes, I'll be explaining the training GAN model. And here, first we create an output directory to store our generated MIDI files, which is named as out. Then we uses number of epochs, which are 2 lakhs, which we can increase as we want to, which does the total training iterations, and the number of samples processed in each training steps is the batch size, which is 35. We can increase the batch size to get a more stable learning GAN model. And the next we uses the two loops. For the first outer loop, it runs for 2 lakh epochs, and for the inner loop, it processes each song and its chromas feature. And we use the zip folder we used. It pairs each song with its chroma feature from the zip files. And the next we goes is the chromas reshaping. Where we do is the original chroma shape is in the ratio of 1000 time steps and 12 pitch classes. And after reshaping, it goes to 250 segments and in the form of 12 into 4 features. Then is the batch processing. In batch processing, we take the song length of 250 and batch size of 35. The first iteration will be song in the ratio of 0 ratio 35, and the second iteration it takes the song is in the ratio of 35 ratio 70. And the model training steps, in the model training steps is it what it does is updates the discriminator first, and then updates the generator, which provides the input data to the model and returns current loss value. And how we save these samples, which we do is as it saves the sample, the value to every 1,000 epochs and generates new music samples using current generator. And at last, we use the sample space of batch underscore size, as you can see, to the feature dimension. After reshaping the time steps and note ranges gets in the form of into two, and after threshold, binary piano roll will work. And the final MIDI file, which is one to the thousand every 1,000 epochs, will we get every file. As you can see in the screen share, we get from zero to we start from 0 to 1,000 and 2,000. For every 1,000, we get a MIDI output file. And the process flow is nothing but we load and pre-process song, which is chroma data, train discriminator on real and fake samples, train generator to fool discriminator, and periodically generate and save new music for MIDI files, and repeat until reaching the number of epochs we have entered. And here we training happens in batches for efficiency, which generates new MIDI files for every 1,000 epochs, as I repeated, which uses both song data and chroma features, continuously updating model parameters. And as we all know, the output file we get is as MIDI files. So that's how the GAN training model works here. And over to Prabhat.
So I will be explaining for testing. I will be using a different data set of MIDI files. So first of all, we call the get song functions to load and pre-process the MIDI files from the classical music MIDI directory. It converts MIDI file to piano rolls. Extra, it uh, Chroma features extract the piano rolls using get chroma function. It stores these features in test chromas. Now it checks whether a directory exists. If it does not exist, it creates the new one. Now we initialize the counter by I by 0. Uh, in the for loop, it iterates over each chroma feature set in test chromas list. And next, it converts the current chroma feature set to a numpy array for further processing. Now we adjust the shape for the generator. In the test chroma equals to test chroma, it ensures the chroma feature array's length is divisible by num time steps by truncating extra rows. In the np.float test chroma.shape, it calculates the total number of full segment that fits into an array. Test chroma equals to np.shape reshapes the chroma feature array into the 2D matrix where each row represents a segment with num time steps frame. Now we are generating the samples. Sys run command feeds the reshaped test chroma into the generator to produce synthetic shapes. Z placeholder for input noise or feature data. Now S equals to np.reshape of out samples reshapes the generated sample into a matrix where each row corresponds to a range of nodes. Now the purpose of doing is that it prepares the output for post processing and visualization. And C equals to np.reshape reshapes the chroma features into their original format for comparison and visualization. Now for thresholding part, we are checking thresh underscore s equals to s greater than equal to 0.5. It binarizes the generated sample using the threshold of 0.5 values that are set to true. Now thresh underscore s np dot transpose function transposes the binarized matrix likely to match the expected format for MIDI conversion. Now PLT figure function creates the large figure for visualization. Same PLT dot s subplot prepares the first subplot to display the generated sample. PLT dot in show displays the reshaped generated sample as a heat map. PLT dot subplot prepares the second subplot to display the chroma features, and PLT dot in show displays the reshaped chroma features as a heat map. PLT dot pause pauses the briefly to allow for real time visualization during iteration. Convert to MIDI and save. Now reverse piano roll uh, converts the binarized piano roll back to the pretty MIDI object. Convert back function reverses any transformation applied during pre-processing. Test.drive saves the resulting MIDI file in the converted directory with a sequential shape, and I plus equals to 1 increments the counter for naming subsequent output files. The code processes a set data sets of MIDI files by loading and extracting chroma features, feeding them to the generator and create a synthetic output, and visualizing and saving the outputs as MIDI files. Thank you.
Ma'am, I'm gonna share what out files, like I'm running the code right now, and this is the out file. Yeah. So this is the out file that we are having, as we have inserted. So this is the first one. I hope you guys can hear the sound. And ma'am, it is processing for every 1000. So now it is still generating, and the code is still running right now. So this is how better it looks. And ma'am, one more thing, when Prabhat said that we have taken another data set, so this gives the converted MIDI file after taking one more data set, and this is I'll play right now. So yeah. Yes, ma'am. So, we're done.
So what is the percentage you completed? Yes, ma'am. அப்படியா?
And we have
எனக்கு எதுவும்
completed
வரலையே.
the 40% of the of our project in this model, and a little bit of a pause was in the project cause of the resources we are not getting. So we are getting the resources now, and it will be completed till the next review. It will be completed the whole model, and we will be able to present you with a like UI presentation if possible.
Okay, we'll try to complete the pending modules. So what is the portion pending? Hello. Yes, sir.
The
Yes, sir. Yes, sir. I am coming, sir. I am in AB2. I am coming, sir. 2 minutes. Thank you, sir.
yes, ma'am,
Okay,
the
fine.
major
You complete the
portion.
remaining portion.
Yeah.
We'll schedule the review to after you share the data. Okay, and what is the portion you completed?
Yeah, the 40% portion is completed, ma'am, and the remaining is the UI and
Yes,
the
sir.
other instrument parts.
Yes, sir. I'm coming, sir. On the way, sir. On the way, sir. I'm coming. I am in AB2. I am coming, sir. Okay, complete the remaining portion. I will share you the other formats. You send me a message, whatever you completed. Okay,
Okay, ma'am.
Okay, ma'am. Okay, ma'am.
fine. We'll
Thank
end the
you, ma'am.
meeting.